welcome again to a new lecture of solar photovoltaics principles, technologies and materials. So, we have been talking about, we have initiated our discussion on thin film solar cells after finishing the Gen 1 solar cells, which are primarily based on bulk materials, that is silicon and gallium arsenide, and we will continue with our discussion on these thin film solar cells. So, just a brief recap, very brief recap. So, in the last lecture we talked about gallium arsenide based solar cells. We looked at their design and what are the considerations that are involved in making them better. They have efficiency between 26 to 29%. So, this is for single junction and this is for multi junction. Then we moved on to thin film solar cells. And we were just talking about the motivation behind these devices, and the primary motivation is reduction in material cost by reducing its amount. Now, let us move to the technical contents of. So, we begin our discussion with amorphous silicon solar cells. Amorphous silicon is not a technology of the day, but it is important to see what it was when it was being used. So, we have amorphous silicon solar cells, which are basically thin film based. Okay. So, amorphous silicon basically has we plot the difference between absorption coefficient as a function of energy. If your crystalline silicon has band gap of something like that, and this is its let us say the coefficient. The amorphous silicon has a coefficient which is significantly higher. So, this is, you can say, is amorphous silicon, and this is you can say is crystalline silicon, and this is generally hydrogenated to passivate the bonds, but this is what. So, amorphous silicon offers you much higher absorbance as compared to bulk silicon cells. So, if you look at the design of these solar cells, it is very simple. It is not a, it is instead of p-n junction, it is like a pin kind of junction. So, if you have a glass substrate, so you begin with a glass substrate. So, this is your glass substrate, all right. So, this is glass and the light comes from here. So, this is where the light comes from, okay, light. Next to it is we have a tin oxide layer. This is conducting. So, this makes a electrode, or we say contact. Okay. Next to this tin oxide, we have what we call as textured tin oxide. And then we have what we call as a silicon in three different forms. So, we have the first layer of silicon somewhere here, then we have second layer in between and third at the bottom. The first layer is generally called as P silicon, this is I silicon and this is N silicon. So, we make a p-n junction, but in between p-n junction we put an intrinsic silicon layer like a depletion region, wide depletion region. So, p-n junction's job is to provide the built-in field, okay, the band bending, because the moment you have P and N, Fermi levels have to align. As a result, you will have band bending. I silicon is the region where most of the light absorption and carrier generation takes place, and this whole thickness of this stack is about 0.5 micron, about, right. And then we have on this side a aluminum contact. So what we do here is we have a glass substrate. On that we deposit tin oxide first. On tin oxide we deposit some other oxide layer. In this case it happens to be tin oxide, but it could be some other oxide. Then we have p-type silicon layer, then we have intrinsic silicon, then we have n-type silicon layer, and then we have aluminum back contact, and the light comes from the substrate side. So instead of gallium arsenide and silicon where the light was coming from the top, here the light is coming from the back side of the substrate. So this is basically what we call is a super straight configuration. Super straight configuration. Light can also come from the other side if you have a transparent electrode on top, and that is a possibility. Instead of, if you replace this aluminum contact by a transparent electrode, then the light can come from the top, and then you replace this transparent electrode on glass with a non-transparent electrode. So that is also a possibility in. So generally, and so you can have two configurations. The first configuration can be the substrate followed by a transparent conducting oxide, followed by the photodiode, which is the pin diode, followed by a metal. Okay, so this is glass, this is TCO, transparent conducting oxide, this is pin diode, and then you have a metal contact which also acts as a reflector. So light comes from this side, this is light. So light goes in, gets absorbed on the way, and it also gets reflected from the back metal contact. So this configuration is super straight configuration. That is what we saw in last slide. And other configuration is you have a substrate, glass, on top of this you have a metal which is a reflector, then we have a pin diode, and then we have a TCO. TCO is transparent conducting oxide, and in this case the light comes from this side, and this is called as substrate configuration, the typical configuration that we have in solar cells, in the silicon solar cells and gallium arsenide solar cells. So this is what it is, and the pin diode is basically this is what is pin, P I N, and this is all silicon, P silicon, I silicon, N silicon, but it is in thin film form, about half a micron thick roughly. Okay. So as I said, there are various configurations which are possible here, and this can also be used to make multi-junction solar cells, because silicon makes a solid solution with germanium. So if I go to next page, also possible to make multi-junction, because silicon makes a nice alloy with germanium solid solution, and silicon band gap is 1.1 eV, germanium band gap is about 0.67 eV, and the band gap can be tuned. So the way you do it is, you have a glass substrate, so you have glass, then you put a TCO, then you put a pin. So this is the first pin that you put of silicon, okay, and then you put a intermediate layer. You can put an intermediate layer, or else you can put another pin. This another pin is basically this is pin 2, so whose band gap is lower than the pin 1, and this pin 2 is essentially silicon germanium alloy. And so silicon germanium, this silicon has a band gap of 1.1 eV, and silicon germanium has a band gap which is lower than 1.1 eV, between 0.67 to 1.1 eV depending upon the composition. And then on the top we put a metal deflector, and which is also a contact. As I said, in between it is possible to put a layer also, which will alter the design, which is a different layer in. So you can isolate the two cells. It is possible to do that, but it depends upon the type of the design of the solar cell. So it could be a separator which can be possibly put in between. Now this solar cell basically allows you to absorb. So you, since band gap of this layer is higher, light comes from here. So this is light. So this allows you to absorb lambda short wavelengths, and in this case you absorb lambda long wavelengths. So this is a, so silicon, amorphous silicon design allows you to make a multi-junction solar cell with sort of bilayer or trilayer structure depending upon how many stacks you want to make. So, and generally these as we will see later on also, we will look into the reasons. The silicon and silicon germanium, silicon, amorphous silicon is always denoted by letter H in front, and similarly amorphous silicon germanium will have a letter H in front, and this basically it means that it's hydrogenated. Okay. So it has been exposed to hydrogen, and we will look at the reasons of why this is done. This is basically done to reduce the dangling bond density in the solar cells. And these solar cells are generally made by, so these are thin film solar cells. So there are certain deposition methods which are used to deposit thin films. So generally these are made by using CVD or chemical vapor deposition methods. This chemical vapor deposition methods are basically, so I mean I will just give you a schematic. You have a chamber in which you have a heated substrate. So this is a heated substrate, let us say. And this is a chamber which is under vacuum or some protected atmosphere. So you have reactants which come from this side, which are basically precursors. Okay. These precursors, when they arrive here, they react and leave. So silicon will get deposited here. So silicon will come down, and this may have, you know, silicon along with the dopant, along without the dopant, and so on. So appropriate precursors have to be chosen. So when they react with each other, the chemical reactions occur, which allows the silicon to be deposited on this substrate. So you have deposition of silicon, and the products, byproducts will be taken out. So these are byproducts which are undesirable, right, reaction products. So silicon will be deposited, everything else will go out, and this happens. So this is called as chemical vapor deposition, because chemicals come into the chamber. They are in vapor form over a heated substrate where they react with each other, and the chemical reaction takes place such that the silicon is deposited on top of the substrate and the byproducts go out of the system. This allows you to deposit large area thin film. So large area substrates can be deposited with uniformity. and they have reasonably good deposition rate. So, they are not very slow processes. So, the deposition rates of the order of few angstroms per second can be deposited. So, you are looking at so depending upon the type of CVD process, CVD can be plain CVD, it could be plasma assisted CVD, it could be microwave CVD. So, there are various things that you can do with CVD process. So, for example, during the reaction chamber to accelerate the reaction, you can create you can create microwave atmosphere, you can create RF atmosphere. So, where you can create electric fields. So, all sorts of possibilities are there. So, the different types of CVDs, they give you deposition rates anywhere between 1 to 50 angstrom per second, and they give you good quality pin junction on the glass substrate. So, essentially the precursors in this case happen to be, generally in case of silicon, it happens to be SiH4 and hydrogen as a carrier gas. So, these are two precursors which are generally used in case of for example, RF CVD. Substrate temperature is of the order of 150 to 300 degrees centigrade, or maybe 400 degrees centigrade depending upon the type of CVD. So, these amorphous silicon solar cells have one issue which is called as, when they are, so they have a issue called as light induced degradation. What happens is that so if you look at the power output as a function of light soaking time, let us say this is the stabilized power output, and this tends to reduce as a function of light exposure before it stabilizes further. Okay. So, there is a reduction in power density that comes out of the solar cell as a function of time, and this is due to a effect called as Stabler-Wronski effect. Okay. Essentially what happens in this effect is, in this Stabler, so upon light exposure, defect density in amorphous silicon increases, and basically what happens is that it damages the silicon hydrogen bonds. After amorphous silicon is always hydrogenated to passivation, for passivation, because amorphous means, so I will come to that in a little while, and this leads to reduction in efficiency of up to 30% reduction in about 6 months, and the fill factor goes down from 0.6 from 0.7 or higher. So, initial value may be 0.7 or higher, then after degradation it goes down to about 0.6. So, what is this thing about silicon? You see, silicon has normal silicon has this tetrahedral bond. So, you have each silicon atom coordinated by 4 silicon atoms. Okay, it has tetrahedral coordination. With sp3 hybridization, right, just like diamond. Okay, it has a diamond cubic structure. So, in case of monocrystalline or polycrystalline solid, each silicon atoms has 4 neighbors. As a result, there are no dangling bonds. There may be some dangling bonds at the surfaces and at the cracks, etc., but by and large the defect density is lower. So, defect density in terms of dangling bonds is low for monosilicon, right, or crystalline silicon. However, for amorphous silicon, there are, since you do not have a crystalline network, all the bonds are not satisfied. So, silicon needs a tetrahedral coordination, but it is incomplete at many places. So, there are missing bonds. So, you can have situations where you have this silicon atom, it has one bond, it has another bond with another silicon, but this bond is missing. Similarly, this silicon atom, it has one bond here, it has one bond here, but this bond is missing. So these missing bonds, these are basically missing atoms. You can say missing atoms, and these are nothing but dangling bonds. These dangling bonds can reduce performance because they act as traps, they will absorb the charge carriers. So, what we do in silicon is that we do hydrogen passivation by exposing silicon to hydrogen. So, that is why extra hydrogen is put in during manufacturing. So, hydrogen passivation, what it does is that it creates these hydrogen bonds. So, it bonds these hydrogen. So, this leads to what we call as, so these hydrogen atoms at these places, they lead to passivation, and as a result they reduce the defect density is so hydrogen passivation basically reduces defect density, and this improves the performance. So, if you plot, for example, the defect density as a function of hydrogen deficit, the defect density as a function of hydrogen deficit, it tends to increase like this. So, this is a sort of a logarithmic plot. So, somewhere here it would be 10 to the power 20 per cc, and this would be about, I do not know, 10 to the power 21, and these defect densities would be of the order of 10 to the power 18, 10 to the power 19, and then 20 per cc. Okay. So, this is how it tends to increase. So, at when the hydrogen and this is on a logarithmic scale. So, for one order of magnitude there is a huge increase in the defect density if you have less hydrogen in the system. So, this is what hydrogen passivation does. So, in case of so if you put it in terms of band diagram, for crystalline silicon the band diagram is like this. Okay. So, this is conduction band, this is valence band, all right, and this is energy. There are no mid gap states or less mid gap states. So, this is less mid gap states, no or less mid gap states in C silicon. But when you do the same for amorphous silicon, in amorphous silicon, so of course, in amorphous silicon what happens is that this is, so of course bands are not very well defined, but let us say if these are bands in amorphous silicon, there are these tail states in these systems. So, these are tail states. So, this is for amorphous silicon, and these tail states are nothing but due to dangling bonds, and this is, they reduce by hydrogen passivation. And so you can say that if this is before passivation, after passivation it is going to look like this. So, this is after passivation is what, so this is what it is going to look like after hydrogen passivation. So, that is why amorphous silicon is always noted as amorphous silicon H. This is hydrogenated amorphous silicon with lower defect density. So, in case of unpassivated, so you have unpassivated, this is called as unpassivated or unhydrogenated silicon will have densities which is larger than 10 to the power 16 per centimeter cube, whereas passivated silicon, amorphous silicon will have a lower than 10 to the power 15 or 16 per cc, much lower. Okay. So, but however, since amorphous silicon has it's amorphous, there are generally, in comparison to C silicon, the tau n and p are roughly 10 to 20 microseconds, very small as compared to, so small as compared to C silicon. The, we can say, lifetimes etc. are lower. So, this is diffusion lengths are of the order of 0.1 micron. Mobilities are also very low. Electronic mobilities of the order of -2 to +1, then -2 to 10 to 1 centimeter square per volt second, and hole mobility is -3 to -2 centimeter square per volt second. So, these are the issues in case of. So, the methods that is generally employed. So, basically the methods to improve amorphous silicon solar devices, one is to control the degradation. So, basically you do passivation, right, which means you put in more hydrogen within the system and improve deposition, all right. So, improved processing and passivation will lead to less degradation. VOC is generally improved by using a wide band gap emitter on top. And if you use polysilicon emitter, it is basically p type. Okay. JSC is generally improved by hydrogenation. So, if you convert A silicon to A silicon H, the response to blue light improves. So, more blue light is absorbed if you put in hydrogen in the system, and then of course you can use of multi-junction and light trapping methods. Okay. So, this is how one can improve these solar cells. This is where we finish our. So, for example, there is one thing you can do for multi-junction is, if you use a multi-junction design, if you look at the quantum efficiency of solar cell, if you engineer a band gap in such a manner so that you are able to use higher band gap in the top layer, so that they give you certain quantum efficiency. You are able to use the intermediate band gap in the middle layer, so they give you quantum efficiency in this region, and then you are able to use shorter band gap in this region, then they give you quantum efficiency. The overall quantum efficiency could be something like this. So, this could be, sorry, so this could be the overall quantum efficiency. This is overall, this is junction 1, this is junction 2, this is junction 3, and you can see the band gap will, and this will be Eg decreases. So, this is your lambda. So, higher wavelengths are absorbed by smaller band gap, lower wavelengths shorter wavelengths are absorbed by higher band gap, and that is how you can make a multi-junction design with amorphous silicon solar cells by using germanium as a material to make solid solutions. So, amorphous silicon solar cells have efficiencies of the order of, let me give you the numbers. So, amorphous silicon solar cells have efficiencies of the order of 10%. Okay, so this is what we have done about amorphous silicon solar cell in this lecture. We will do the remaining part in the next lecture. Very little is remaining, and we will discuss other thin film technologies in the next lecture or so. Thank you very much.